Hello community, finally! Let's talk about the latest AI research development. Can we go non-token? Well, all our AI foundation models currently rely on token representation. And there's already a symmetry breaking happening because we have continuous real-world data, and what we do, we chop those data up, we discretize it, we use it as tokens, and then we calculate around with our little tokens. And you might ask, is this the future of AI? And let me tell you, maybe not. So, this token fragmentation limits here really our AI ability to learn. Because real-world knowledge goes beyond statistical correlation. We want to maintain a semantic coherence if we move across our modalities. We want to capture some fine-grained spatiotemporal dynamics. And we need to perform robust, complex causal reasoning finally across the models here in our modalities. So please, why don't we have this right now? Now, the authors of today's study from Johns Hopkins University, they argue all those limitations are inherent to the tokenization paradigm of our current AI. And those authors tell us, hey, this is not solvable by just merely scaling the model size or the data set. So it doesn't matter if you go to, billion, trillion, quadrillion token. No, it does not help. This is a limitation that is at the base of our model, at the core of our model. So what can we do? We need a spark of genius, and I know you are here exactly for this spark of genius. So one sentence to open your eyes, and I will start with a little history lesson. Yes, it's about history time. So at the beginning. At the beginning, we were happy if LLM could generate one sentence that made sense. And then it could generate multiple sentences. And we were saying, yes, it's fantastic, that made sense. And in reality, it was just a pattern of a copy and paste AI. But who cares? Then our sentences were constructed of words, and so it made sense that our words and our subword tokenizer, we introduced those kind of tokenizers to convert our human sentences to vector objects, to embedded tokens, now at the input of our transform architecture when we enter here the first layer. But then towards outcome-driven, physically grounded representation is that we noticed that our AI system started to fail. Why? Because physically grounded representation is what we call a real-world experiment. And guess what? Up until now, we just talked to our AI. The AI just copied the internet. This was just here a beautiful semantic description, a linguistic interpretation of something that's really happening in the real world. But it was not the real thing. It was just here, maybe a little bit polarized by a particular description of humans. So, our sentences were LLM generated and reproduced as long as we wanted semantic representation. Like, for example, social media, the gossip. We just wanted to chat a little bit with our friends. But AI failed completely to understand the real world, the dynamic, the dependencies, since it had only those stupid semantic description of it. And then suddenly we had this crazy idea that we want AI to manipulate now two-dimensional arrays. We call also in the professional speak, images. And we started to describe those images, no? We went into the training data, into pre-training for a vision language model. But those descriptions were generated by millions of different people. They were not coherent. Every human focused on different aspects of the image. Everybody described details in different ways. And the outcome was just horror, pure horror. So what we want to achieve now? We want to go beyond purely statistical, fragmented token representation to a real-world, outcome-driven, physically grounded representation to achieve some genuine multimodal understanding of our AI with some great causal reasoning and a real, robust, complex real-world interaction for our robotic actions. But we don't have it right now, because today, our multimodal models fail at multimodal understanding, have no coherent causal reasoning crossing the different modalities, and our vision language action model, or our robots if you want to call them, have to be trained on each and every little single tiny little irresponsible aspect of the real world interaction because they are simply too stupid to learn it themselves. We have not given them the right basis because we have given them tokens. So, yeah, if you want to know more about tokenization, text tokenization, image tokenization, and video tokenization, this is here, this information for you. If you want to see this live from 2 and 3 years old video here about byte pair encoding tokenizer, we built here, we code our out tokenizer, we built here complete input data pipeline for BERT. We have here new BERT tokenizer on purely scientific domain knowledge. So we have an extreme domain specialization in the tokenizer. These are the video for you. And do you remember from Meta, I don't know, half a year ago, this sudden blob of information about a byte latent transformer, where we calculated also the entropy of the next byte as I showed you in this video? No, you forgot it. Never mind, the core is now, in the current development of the next gen AI, we want to get rid of the reliance here on the token representation. Because our AIs have shown that their understanding is absolutely superficial, non-existent for some models, because it's purely based on statistical correlation learned from some massive dataset that describe events. My goodness. So, yeah. Talking about description and representation and attract this short remark, I had just a conversation with somebody and said, hey, where is the code in your video that I can take, that I can copy, that I can use? And I said, here in the video, you find the encoded knowledge of multiple new research papers. And the person said, no, it's just you talking, you're just presenting paper after paper. But where's the code that I can take away from you? And I said, yeah, this is the code, but this is the code for your brain. What you are looking for is the code for your Python compiler. But I would like to give you the code for your brain so you can learn faster. And this is where suddenly our conversation ended and never heard again. So we go on now with this video. So tokenization has the effect. It fragments continuous real-world data. It creates artificial boundaries. This is what they are telling you from Johns Hopkins University. And it forces here our foundation models, our AI models, our vision language model, our language model to relearn physical principles and domain knowledge from scratch through statistical correlations again. My goodness, this is boring and it struggles with maintaining semantic coherence across modalities. And I showed you the reason why. And it struggles to perform some robust causal reasoning. And this is the reason why I have, I don't know, a dozen videos about how to improve AI reasoning, because we are still working here with tokenization. Okay, beautiful. So I hope you are now motivated to develop here a representation that can overcome this limitation and enable here to the foundation model to achieve a more profound understanding of the world. And you remember this study. This is here from May 2nd, 2025 by Google DeepMind and Carnegie Mellon University, the title Improving LLM Planning with Action Sequence Similarity. And this is, and I told you this at the time, a very important paper. I highly recommend this. I made a particular video about this just 2 days ago. Great. And I told you that Google discovered that it is not worth anymore, if you want to improve the AI reasoning capability, that you stay within the task description vector space, that you are looking here at task description specific features, performance indicators here. Because a task description is not what will help you to solve your task. What you need to search for is action sequence from the planning process, so a sequence of actions to arrive at the correct solution. Google said here, we developed here a beautiful new process here, how we can do this. And I showed you in my video here that instead of going now in a vector space that we go normally with a task description similarity computation here in, I don't know, 758 dimensional vector space of our embedded vectors, we develop now a new vector space where we have now our action sequences as the main element, as the main embedded vectors in this vector space. And now we calculate here the similarity. But we calculate the similarity of a given action sequence of our LLM in the first round, and I showed you it's a two-step process. And then we look at all similar action sequences here in the vector space that have a similar part, at least one similar part in it, and then we report this back here for our in-context learning. But you see, we build now different vector spaces with different representation. We don't go for descriptive, but we go for solution-oriented action sequences. And Google told us, hey, we have some significant performance increase with this methodology. You see, here we already saw the first indicator. Hey, something is going on. Something is moving away from the old classical structure. And here we have now the study I would like to show you. Here's Johns Hopkins University Department of Computer Science, beginning of May 2025. And they have a position, and they publish this and say, hey, foundation model need digital twin representation. So remember Johns Hopkins, famous for medical, hospital and everything. We come back in this in a second. And they situate the paper here in a rather niche of representation learning for foundation models, particular for multimodal and embodied AI, robotic AI. So they really go to the research bleeding edge here for AI, and they say, over there, if we do multimodal and embodied AI, we encounter so many problems, and they say those problems here kind of have to do with the token representation. They have an idea, they have a solution. So before the foundation model now see, let's say, a video sequence or anything else, but let's stay with a video sequence of a ball rolling down. And they say, imagine we would now have here another AI watching here this video. And this AI would be a digital twin construction module. So we would able to build here a computer simulation of the content that we see in the video. And this DT construction model identifies this as a ball, estimates the geometric properties of the ball, the shape, the size, the angle, tracks here the continuous motion, the velocity, acceleration, and even embed known physical laws, here conservation of energy, and into this rolling ball observation that it now try to rebuild here in a virtual computer simulation in a digital twin. And this is now a new model that we add to our AI repertoire, and we see, wow, with this, suddenly we do not need a verbal description, a semantic lingual description, and now I see a ball, and the ball is rolling down here with an estimated velocity of 2 meters per second with an inclination of 6 degrees, and you get the idea. But we have it already now transformed into a computer simulation. And then we feed here this structured digital twin representation of all the data about the entity states the system is in, the physical parameters we deducted from multiple frames of this video, and we build a relationship graph because maybe a car is passing by or a child is running behind the ball and there's a fast car approaching from the other side. You get the idea, no? So all of this is now a different structured representation that we feed now to the foundation model. So what is the idea? And I want just to give you the idea. The intuition behind all of this is that you provide now the AI with a representation that already embodies now the key aspects of reality and the complete domain knowledge, physics for example, and the foundation model can focus now on higher level reasoning and prediction tasks. Remember, we went away already in one of my last videos from a task description into an action sequence that we need to solve. And this is now an action sequence that comes out of a virtual computer simulation. So you see, it is all converging. All the different research groups around the world, they come together more or less, and they develop here similar trajectory with one convergence. Leading to better understanding, it's about giving the FM, the foundation model here, a better lens if you want to see the world. You do not need now a description of chopped up tokens, but you have now something that is really attuned to the physical. And of course, yeah, we need semantic realities. We are humans. We hear, we talk, we have here different sensory equipment with us. Great. So imagine we would now learn or train here the next generation of AI, the next foundation model, the next best model to come. How will we do this? Would we also copy the internet, just a semantic linguistic description? And then I saw a ball rolling down the street? No. Maybe we go and we say, well, let's say in my department here, We have, I don't know, we have thousands of computer simulation from everything from quantum mechanics, quantum field theory, everything. If you go thermophysics, just if you think about chemistry, I don't know, 10, 20,000 computer simulation that are available for you, that are verified with experiment, real world experiment verified computer code. It is not AI. Think about it as a tool if you want. But now, instead of talking to the vision model, to the foundation model here, without giving it access, we can now do something better. We provide the foundation model a learning capability. We provide access to all the computer simulation at the university or globally. I don't care, whatever, you get the idea. This code, C++, Python, whatever you have, that is really tested 10,000 times in the real world. Boiling water, for example. You know exactly what's going to happen because we have a deep understanding of the physical nature. What is the understanding why it is happening? And now we don't have as human to describe this to the FM, but the next generation of AI learns this simply from our computer simulation libraries or the internet worldwide. You know what? We have also here made this step to a higher aggregation, to a higher complexity, because all this additional knowledge is already encoded in the mathematical formulas, the laws of nature if you want, here in this computation code. So great. What else? Yeah, digital twin representations serve now as the underlying representation layer that encodes now this new property, this new feature, if you want, in a format suitable for the foundation models. I can only show you that most 20% of the paper, 80% of the paper, you have to go there, you have to read it, you have to fight yourself here for an understanding that you see where they are, how they want to improve in the next step. But I think it's important. We now want the next system to train already on the geometry, on the physical property of domain-specific constraints. We don't just want to rely on copy the internet. This is not enough anymore. So we want to generate synthetic data. Yes, of course. But those synthetic data are not from Reddit, are not from Twitter, are not from any other social media platforms from your grandfather. Those synthetic data are coming now from validated physical, physics, medicine, biology, whatever you have, computer simulation. The next generation of AI should learn from validated computer simulation code. Understand that the real world is different to the verbal description of humans. We will apply this, or they already think I've applied this here, this virtual representation of any physical object, of any physical process or any physical system in engineering, in manufacturing, in healthcare, from monitoring, analyzation, optimize here, process structures, physical counterparts, whatever you can think of. And we are talking now about real world physical processes and outcome-driven replicas. So before we let our robots really out in the wild, really in contact with humans, I think it's a good step to go into this complete virtual training camp where the next generation of AI will learn here from these replicas, all physical chemical processes that exist on this world. Because then they learn reality. Maybe another perspective, maybe this helps you. I don't know. I try to give you as many as possible hints that you say, hey, now I got it. A linguistic description of the action in an intensive care unit, in a hospital, in a clinic is not enough data to learn why something happening, what is happening, what is the leading course for things to be done in the way that they are done there. Because you have humans, and we don't just communicate on linguistic and semantic or whatever. We see immediately, if we look at other humans, the doctors and the support staff are trained to understand what could be the medical conditions and so on. So you have all the visual information, maybe you even have some smelly information, who cares? And you have multi-modal knowledge right from the beginning. And maybe it was not the best idea to start out of just simply language model, but maybe if we would start today from a multimodal knowledge base, we would develop different methodologies for the core of our next AI structures. If you want to learn more about this is something that I would recommend. I know it's already from end of March 2025, but it is on the challenges and opportunities of generative AI. Very interesting paper. I highly recommend it if you want to learn more about limitation we encounter today. Let's have a look at the future. We make now a jump. This is now the next level of complexities. If you want to stop the video here, beautiful, no problem. This was the main message. If you want to go further, if you say, hey, I'm crazy enough to listen to this person another 5 minutes, let's have a look what's happening. Today, for me, today recording this video, May 7, 2025, a new beautiful paper published here by the Shanghai Jiaotong University. Sorry to the authors, I don't pronounce your name, but you're all beautiful. I know this beyond theorem proving. This is so important. Formulation, framework, and benchmark for formal problem solving. This is a part that I have not really mentioned a lot of on my channel, but it is so important for better science and engineering and problem solving and causal reasoning. Problem solving, if you think about it from an abstract point of view, a theoretical point of view, is not easy at all. If you really want to develop kind of a mathematical model for this and implement it in a deterministic Markov decision process, this is the paper for you. It has some beautiful GitHub repo. Have a look at this. It encompasses everything from computation, equation solving, mathematical equation solving, example construction, and I think the problem solving ability of an AI is the key to intelligent system. Nothing else. Just generate a plan to solve something, generate here an action plan to be able to solve the complete problem. Now, we do have the informal problem solving that you do daily with your LLM, your prompt, your Python tool, your algorithm, your tools. Beautiful. But the next step is much more beautiful because we have formal problem solving, and this is what they propose here, a deductive formal problem solving mechanism here, where they say, listen, it is not enough anymore to go with the human language. We have to build dedicated LLM systems that go now here on a particular artificial computer language. Let's call them, just by coincidence, Lean 4. And those are Theorem prover software. So we have a formal solution. Here you see the code. And those systems are able to come up with absolutely the correct solution. So it is not anymore that we ask here some LLM, hey, this is the example, do here some mathematical calculation that any pocket computer could do. But we go now here for the real complex mathematical formal problem solving algorithm. And they have now their own LLM because Lean 4, if you've heard it, yeah, it is already the 4th version. So they're in here for several years here developing their own system. So I think this will come in now to our regular AI system. This will be the next step that will be implemented in your next AI, and you will have no idea what's happening to you when an AI is suddenly possible for the AI to come up with absolute correct solution, because it is not anymore stumbling with some multi-token representation and I just calculated the next token. No, it is using here what we as humans already developed in the last, 5, 10, 15 years on theoretical mathematical ideas. Formal theorem proving, what a beautiful idea. Here you see the definition. They start with the definition of what is a problem, then they have here definition what is an answer, what is here satisfiable here, and they go on what is a solution state. So they have a complete deductible formal language development with their own language. And of course they have here a GitHub repo. You see this is just established yesterday. So whenever you go there, you will have already more data and more agents here active for you. Really interesting. I think this is something, if this is integrated in the next generation of AI, I'm dreaming of it. Yeah, Lean, if you're not familiar, a programming language and a theorem prover, a very particular idea that we have, if this will become an integral part of AI, it will be great. One day ago, if we go the next step, if we say, okay, this was a simple mathematical problem solver, now we want to go here, the next abstraction, the next level of complexity, because we want to have fun in this video, not just walk around. So this is where I showed you, hey, if you are a theoretical physicist and you want to learn more about singular function of the expectation theory when we approach here as self-learning AI, you might find this article interesting. And here you have from Carnegie Mellon University and Peking University and beautiful authors, thank you. Now, new forms of representations from context. And they have here a new beautiful proof of very simple ideas, but the way they approach it is absolutely interesting. And they call this contextures. I have even a short comment here, if you find it here on my posts. And I compare this here to the content of my last video where I showed you here the optimization of the LLM action planning space with ICL, with this Google algorithm. And I told you, isn't this a coincidence? Look, it's another perspective, another puzzle that goes in, that comes together now. So you see, this is really the leading and bleeding edge of AI and nothing else. And then I ask you something, and this is really for the next level. Do you see the possibility of an action integral, a path integral like we have in quantum mechanics here, an action path integral emerging in this solution space here of the AI that we are dealing with? And if you are into the mood, there is a video for you waiting on quantum AI, but you get the idea where we are moving. Now, you missed last week the new DeepSeek model release, no? Haven't you? No, I'm not talking about V3, and this is all beautiful, but there was one model. And okay, I have to explain, I love DeepSeek. I think this is a beautiful way. Yes, my American friends, DeepSeek, I think I love DeepSeek a little bit more than I love OpenAI, because they have open source models, and this is great. And they released here their latest model, and this is here from last week. And their model is a DeepSeek Prover version 2 model. And as you can see, 15 watching, nobody knows about it. A prover is not a reasoning model. A prover is not a base model. A prover is not a vision language model. A prover is exactly what we talked about. A prover is a dedicated LLM in the next step here for the next gen, an open source, thank you DeepSeek, open source, so great, designed for formal theorem proving in Lean 4. And I thought, impossible. They already have this LLM. So I'm looking forward for the next model, DeepSeek R2. I can't wait for it, because if they integrated this here with Lean 4, this will be a real interesting model. You know why? If you read the publication here, DeepSeek Prover 2, advancing formal mathematical reasoning. And you might say, okay, this is only mathematical reasoning. No, this is a reasoning change, a new paradigm that we have for all causal reasoning. Everything from finance, medical, logistic, production, engineering. You can use this wherever via reinforcement learning for sub-goal decomposition. Again, one of the topics in one of my last videos. What a coincidence. Everything falls into place in these days. DeepSeek AI, beautiful, beautiful paper. And they give you here beautiful examples, if you're not familiar, that you get an idea what is happening, why they need this here, why they lean on Lean 4. And they tell you here how we do the training. We have here DeepSeek version 3 model, great, the latest model, formalizing here this with a lean statement. Then we have a prover model, solves here the decomposed subgoals. We put everything together in a composed proof. And then we append this to the DeepSeek version 3 original chain of thought. And if they did this before they trained now R2, this is gonna be something beautiful. So, you see what's happening now? AI develops significantly. We don't have anymore based on linguistic token. We have now new formal theorem prover that are integrated in the development of AI system, in the development of our original chain of thought, tree of thought, or maybe whoever does here the next hypergraph chain of thought. So the development trajectory for the next gen of AI is already set. And if I talk about the next generation, I'm hopeful. You know why I'm hopeful? Because I've read this just 2 hours ago. And there is also a new study by Google DeepMind and University of Washington. And they told me, and I had no idea about this, and I thought, hey, that OpenAI bought Windsurf is of interest. Forget about it. What's interesting is we have now code editors and code generators for 7-year-old children. And if you click here on read more, you have here my personal opinion on this, which I have to tell you is simply amazing. A 7-year-old child has now an AI code editor, because what they did, they developed here regarding here best practice on a human-computer interface and UI interface definition here, a Scratch Copilot supporting youth creative coding with AI. So my goodness, if you are either the father of a 7-year-old child or if you are a 7-year-old, you have now AI code editors that are particularly designed for your age group, for your particular age, 7 years. And they help you to code whatever you want. And the topic is here, democratize programming for children. And on the one hand, I think it's great that wherever you are in this world, you are a young child, and maybe you cannot afford to go to elite school or any school at all. You have on the internet available that you can learn to code, and you have particular AI code editors for 7 years old, designed for 7 years old, and you can start immediately. And I think this is a great start. So this is great. This is amazing. This is really pushing here the next generation here. Unbelievable forward in understanding, in coding, in logic, in causal reasoning, in AI programming. Wow. But on the other side, I think a 7-year-old child should have some freedom to go out, to play, whatever it wants to do. But if it really wants to learn, and if it really is into coding, the possibilities today with technology are really unlimited. Hey, maybe you found it interesting, maybe you subscribe. If yes, I see you in my next video.